In the next few minutes, I'll show you what a digital signature actually is, why we sign the hash of a message instead of the message itself, the exact mechanics of signing and verifying with a public-private key pair, the difference between encryption and signing. They look similar but solve completely different problems, what algorithms power modern signatures, and the everyday systems that would completely break if signatures didn't work. Welcome to Defense Stack. We produce one concept a day, and each one stacks on the last, building the framework for security together. Let's dive into digital signatures. We ended episode 3 with 2 open problems. When you receive a message, how do you prove it came from who it claims to? And how do you detect that it wasn't tampered with along the way? Both are real problems, and both have the same solution. A digital signature is a small piece of data attached to a message that anyone in the world can use to verify 2 things. First, that the message was authored by the holder of a specific private key, and second, that the message has not changed since it was signed. Encryption gives you privacy. Signatures give you authenticity and integrity. The first thing to understand is that you do not sign a whole message. You sign a hash of the message. There are 2 reasons. The first is speed. RSA operations are slow, especially on big inputs. Signing a 50 megabyte file directly would take forever and waste enormous compute. Hashing the file first reduces it to 32 bytes, and signing those 32 bytes is fast. The second reason is more subtle but more important. RSA on raw arbitrary data has a bunch of security gotchas that disappear the moment you sign a fixed size hash instead. So every modern signature scheme works the same way. Hash the message, sign the hash. To verify, hash the message yourself and check the signature against your hash. Mechanically, here's what signing looks like. Alice wants to send a message and prove she wrote it. She hashes the message, a 32-byte fingerprint. She runs that fingerprint through a sign operation using her private key. The output is the signature, which she ships alongside the message. Now Bob receives both. To verify, Bob hashes the message himself and runs the verify operation using Alice's public key on the signature. The result is either valid or invalid. If even one bit of the message changed in transit, the recomputed hash won't match the one inside the signature, and verification fails. If the signature was forged by anyone without Alice's private key, the math doesn't work, and verification fails. This is the part that confuses people the most. Encryption and signing both use a public-private key pair, but they go in opposite directions. To send something private to Bob, you encrypt with Bob's public key, and only Bob can decrypt it with his private key. To prove you wrote something, you sign with your own private key, and anyone can verify with your public key. The keys aren't the same in those 2 scenarios. Bob's pair is used for receiving private messages. Your pair is used for asserting your identity. Many people have separate key pairs for each purpose. The important thing to remember, encryption uses the recipient's public key. Signing uses your own private key. There are several algorithms doing the actual signing math. RSA from episode 2 can be used in reverse. Instead of encrypting with the public key, you sign with the private key, and verification works because anyone with the public key can run the math forward. RSA signatures are everywhere, but they're slow and large. Typical signatures are 256 bytes. The modern alternatives are based on elliptic curves. ED 25519 and ECDSA both use much smaller keys, 256 bits instead of 2048, and produce 64-byte signatures that verify in a fraction of the time. New SSH keys, TLS 1.3, and modern JSON web tokens almost all use elliptic curve signatures now. The most consequential application of signatures is software signing. Every time your phone or laptop downloads an update, the binary is accompanied by a signature from the vendor's private key. Your operating system has the matching public key built in. Before the update runs, the OS hashes the binary, verifies the signature, and refuses to run anything that doesn't match. macOS Gatekeeper does this. Windows has code signing baked in. Linux package managers verify GPG signatures on every package. If a binary is tampered with, even a single byte, the hash changes, the signature no longer verifies, and the OS rejects it. This is why a compromised vendor private key is a catastrophic event. The attacker can sign malicious updates that the world's machines will accept as legitimate. The SolarWinds attack in 2020 was exactly this. Attackers got into the SolarWinds build pipeline and slipped malware into a legitimate Orion software update. Because the malicious build was signed with the real SolarWinds private key, 18,000 organizations downloaded it through normal update channels, and their own operating systems happily verified the signature and ran it. The math worked perfectly. The trust model failed because the key got stolen. Software signing is just one use. TLS certificates, which we'll cover next episode, are essentially signatures from a trusted authority asserting that a specific public key belongs to a specific website. JSON Web Tokens, the JWTs that authenticate billions of API requests every day, are hashes plus signatures. Change 1 byte and validation breaks. Git commits can be signed with your GPG or SSH key, so anyone looking at the history can verify who actually wrote each commit. Every cryptocurrency transaction ever made is a signature. The blockchain is literally a public log of signatures plus the messages they signed. Signatures prove that whoever holds a specific private key signed a specific message. They do not prove that the public key actually belongs to who it claims to belong to. Anyone in the world can generate a key pair and put any name on the public key. If Eve generates a key pair, calls it google.com's key, and convinces your browser to use it, every signature she produces will verify perfectly with her own public key, even though she's not Google. The signature math is honest. The naming is the weak link. Tomorrow we close that loop with certificates, the system of trust that makes a public key bindable to a real-world identity. Tomorrow we cover the second half of how the modern internet actually trusts anything. Certificates wrap a public key together with an identity, a domain name, a company name, an email address, and the whole package is signed by a trusted authority. Those authorities are themselves signed by even more trusted authorities, all the way up to a small set of root keys your operating system was shipped with. When your browser connects to a website it's never seen before, this entire chain gets verified in a fraction of a second using the signature math we just covered. Once we have certificates, we have everything we need to assemble TLS itself in Episode 6, the protocol that secures essentially every connection your browser makes. That's the end of this concept, but each video stacks on the last. Subscribe, and we add the next layer tomorrow. So that's digital signatures, the combination of hashing and asymmetric encryption that gives you authenticity and integrity, the algorithms, RSA and the modern elliptic curve options that do the actual math, and the systems built on top of them that quietly run essentially every authenticated interaction on the internet. 4 episodes in, we now have privacy, integrity, and authenticity. The one thing missing is identity, proving that a public key actually belongs to who it says. Tomorrow we close that loop. Thanks for watching.